recording because now that I think about it, I believe we possibly did not finish 19. So hello, we are now in the second half of week 13, and I'm going to share my screen. And we have been working on sampling methods and sampling distributions. We definitely did the Skittles example because I remember my Skittles. I love my Skittles. We did this, we skipped this, even though I did it in my class yesterday. It was quite interesting, but anyway, we kept going. We did some random sampling here. We did this, we skipped this, we did that, we skipped that. No, we did that. We did this as well. We did all of this. We did this, we did this, we did this. We possibly skipped that. We definitely did this. And no, we did everything. We certainly did. So we are now moving on to chapter 20. So chapter 20, testing statistical significance. This is kind of like a culmination of essentially a first class in statistics. When I teach stats, more advanced courses in stats, but not too advanced, still a 100 level, but for math majors. Statistical significance testing is really where the course ends because everything that we've done has been building up until this. So let's start with the following group activity, Happy and the mirror. To test whether she could recognize herself in a mirror, an X was placed on the forehead of Happy, a 34-year-old Asian elephant at the Bronx Zoo. No X's were harmed in the making of this experiment. Just be aware of that. Now, after observing the mark in a mirror on 12 occasions, but never before, Happy used her trunk to touch the mark. She never touched the other side of her forehead, which had been given a transparent X. What the hell is that? So after observing the mark in the mirror on 12 occasions, but not before, she used her trunk to touch the mark. I assume that means the mirror, or does she touch the mark on her own? She never touched the other side of her forehead. Oh, I see. Okay. So in other words, in the mirror, there's two X's. There's the one that is someone chatted something. Maybe they understand what the hell we're talking about here. Lori, we can't hear you. Oh, has Lori been trying to talk? Lori, we still can't hear you. So she never touched the other side of her forehead, which had been given a transparent X. What does a transparent X mean? Anyone know what that means? What's transparent mean? Transparent means...
Doesn't it mean like in front of you?
See-through.
See-through. But I'm not really following that.
Like, let's say tape, like make an X with tape. You know how it's transparent? It's see-through.
Yeah, but the X that they put on her thing was also like
the X that they put on the other side looks like if it's white. So maybe they're trying to say that the elephant saw color, but not transparency.
Maybe. I don't know.
That's what I get out of it.
All right, well, let's skip this one. Let's do a different one.
I'm worried that this makes no sense.
Yeah, let's do a different one. Okay, so let's skip that one. That was silly. Not silly, but it was not written well enough for me as the teacher to understand what was going on, so let alone the students. Although maybe some of you did get it and I didn't. It's always possible. Let's try this one. The 1986 accident at the Chernobyl nuclear reactor brought about concern that the radiation might cause mutations in the genes of humans and animals that would be passed on to offspring. This is before most of your time, but I certainly remember this happening. Before the accident, 2% of barn swallows had white feathers in places where the plumage is normally blue or red. The white feathers are caused by genetic mutations. So essentially before the experiment, 2% had genetic mutations in this particular capacity. In a sample of 266 barn swallows captured around Chernobyl between 1991 and 2000, which was after the accident, about 16% had white feathers in places where the plumage is normally blue or red. 16% is certainly an increase from 2%. So the question is the following. Is 16% far enough above 2% for us to conclude that it is a statistically significant difference? And what that means is as follows. A statistically significant event is one that cannot be attributed to chance alone. For example, if I roll a die, a fair die, what's the likelihood that I'm going to get a heads?
50-50.
50-50, 50%, right? If I roll a head, if I roll a coin 5 times, is it out of the realm of reasonable possibility for me to get 5 heads? If you got 5 heads on 5 flips, would you start saying, my God, this coin must not be fair? There's no way that would happen. Would that be a reasonable conclusion from 5 flips of a coin?
I think you'd need more flips because 5, it's not like super normal to get it, but it's also not enough to be like, why is it happening?
And that's exactly the point, right? It's
According to the
not-
law of large numbers.
Oh, look at you,
Yes.
Lori. Woo! Lori, go. Not Lori, I meant Angel.
That was Crystal. She's like my BFF
You're right
anyways.
You're right next
We're like
to me on screen,
twins.
so I meant to say I apologize. But this is the point. Okay, this is the point. It's not an occurrence that would be expected, but at the same time, it's not an occurrence where it's so unexpected that you say, this can't happen, something must be wrong. But if I flipped 1,000 coins and got heads 1,000 times, now I'm concluding, wait a second, something's off here. There's
You
no
need to go to
way-
Vegas.
Well, yeah, but it's not reasonable to get this outcome by chance alone. So that would be a statistically significant event. Getting 1,000 heads on 1,000 flips of a fair coin is a statistically significant event because the likelihood of it happening is so small as to never really happen, or at least not often enough for me to say, oh, okay, didn't see that coming, but not crazy. So the case here in the Chernobyl example is whether or not having a sample of 16% mutations is so far ahead of 2% that we say, okay, something must have gone on here or not. Now, we don't have the math yet for it. It's just a conceptual example. We're going to learn, right? You will learn to decide whether the evidence that the rate of mutations was higher in Chernobyl after the accident is statistically significant, or can it reasonably be attributed to chance alone? In other words, let's say there's a 10% chance that occurred. Okay, 10%. Wouldn't expect it, but it's not crazy. But if it's a 0.000000001% chance that it occurs and it happens, then all of a sudden I might start thinking, okay, something's up here. Okay, so this is the idea of this chapter. It's on statistical significance and specifically testing statistical significance. Is the result crazy enough that I have to start questioning my hypotheses? Or is it possible to have occurred with a high enough probability that I just accept it and move on? Okay, so let's fill in the values that correspond to each symbol in this example. First, n is my sample size. What is my sample size in this Chernobyl example? What is my sample size in this Chernobyl?
266.
266, right? In a sample of 266 barn swallows, right? So n is equal to 266. P hat is the proportion of yeses in the sample. Yes is similar to something along the line of
Equally likely.
no, not equally likely. It's like a success.
Mm.
It's like I'm getting the result that I wanted to get. So out of 266, what percent were the yeses, were the successes, were what I was looking for?
2.
That's not a 2%?
16%?
16%. They tell me right here. Right? About 16%.
Oh, the success is having
having a white
feathers.
in places where the plumage is normally blue or red. That would be a success in this problem. X is the number of yeses in the sample. X is the number of yeses in the sample. How many, not what percent, but how many of the 266 swallows were yeses? So I use my calculator for this, by the way, just so you know, it's not something I did in my head. How many of them were successes?
16% of 20, so
Not of 20. Where does 20 come from?
I mean 2,000.
Not 2,000. That's a year.
I mean
Is it
266.
266?
266. So what's 16% of 266?
You guys hear background noise from my end?
Yeah.
Okay.
So what percent? I mean, what's the number of successes?
I don't think I got the right thing.
42.56.
Right. But of course, we're talking about how many birds, right? So it's got to be a whole number.
43.
So what I just did is I checked the numbers are rounded to see what would round to 16%. And there's actually 2 that would round to 16%, either 42 or 43. Both of them would round to 16%. But because 43 is closer, we're going to go with 43.
That's the
That's a number,
X.
that's a number of successes, right? There's 266 in my sample. 16% approximately said yes. And the number that said yes, we're going to say is 43. Now, what is the proportion that we're comparing our sample to? We got 16%. But what is the proportion that we are comparing our sample to?
The birds that were chemically affected by Chernobyl,
But what number?
2.
that's between 2 and 16.
But what? So what are we comparing it to?
2?
2%. Exactly. Okay, we're trying to compare ours to 2%. Whether or not what we have is comparable to 2%. Does that make sense?
Yeah.
Okay, so the question is our result so far away from 2% that we would question whether 2% still holds? The larger the sample, the closer we expect to be to the true value. So with a sample of 266, the question is, are we far enough away from the true value to question whether this still holds? Okay, so let's, of course, we don't know the answer to that question yet. We haven't gotten that far. We haven't seen exactly the math that we have to do. So here's what we're going to do. We're not going to do that, but here. So this is the sampling distribution for the situation of selecting 266 birds at random from a population where 2% have white feathers and counting the number in the sample with white feathers. Okay, so let's not worry about this binomial. I don't think we covered that, but so we don't have to worry about that. But essentially what this is saying is as follows. What percent had the highest likelihood of occurring? Okay. 0%, 1%, 2%, 3%, 4%, 5, 6, 7. I assume these are the percents. No, these are the number. Oh, I know what they are. Hold on 1 second. I'm going to confirm this for a second.
Number of birds.
The number of birds, right? The number of birds. Yeah, the number of birds. This is the number of birds that had white plumages in our sample. Okay, in other words, we took 266 birds at random. And we saw, and we did the same thing. Okay, so let me start again. Let me clarify what I was trying to say, because I don't think I was saying it correctly. Suppose lots and lots and lots of people took samples of size 266. So you took a sample of 266 birds, and I took a sample of 266 birds, and he did, and she did, and they did, and he did, and it did, and what did. We all took samples of 266 birds. What we have here is the distribution for each of our samples. For example, what percent of the time did we have 5 birds with white plumage? It happened roughly 17% of the time. 17% of our samples had 5 birds with white plumage. And what percent of our samples had 4 birds with white plumage? About 16%. And how many of our samples had 3 birds? About 12%. And how many had 2 birds? About 7%, and so on. Now, how many of the samples had 43 birds like we were projecting? How many of our samples had 43 birds? The answer, none of them. 0 birds, it happened a couple times. 1 bird, 2 bird, 3, 4, 5, 6, up to 13 birds. Not a single one of the samples had more than 13 birds with white plumage. And how many did we have again? 43, right? If this were truly correct, if it was really 2%, this is the distribution that we would expect. We would expect something that looks like this, where 5 occurs the vast majority of the time, 4 and 6 slightly less so, 3 and 5 slightly less so. If this was really correct, how often would you have 46 birds in your sample? Essentially never. Okay, if this were really correct, you would have 43 birds never. And yet that's what we got. So what are you going to conclude? Again, let me say that again. If this were really correct, this 2%, if this were truly correct, I would expect a distribution that looks like this. And in that case, I would never have a sample with 43. And yet I got a sample with 43. What do I conclude?
Graph is wrong.
Sorry?
The graph is wrong.
And why would the graph be wrong?
Because you have a different sample size.
No, the sample says they're all 266.
The graph doesn't show 266.
Yes, it does, right here. The graphs are all 266. Every one of those samples came from 266 birds taken at a time.
What was the other number again? 46?
I got 43 successes. I got 43 birds. So the answer is this must be wrong.
Yeah.
The whole assumption is based upon that 2% of the birds are going to have white plumage. Under this assumption of 2%, this is the graph that I expect. And yet I landed way out to the right. It's got to be that my assumption is incorrect. So I conclude that it's no longer 2%. Because if it was true 2%, I would never get 43. It must be higher than 2%. The results of my experiment do not jive with the assumptions of my hypothesis. What statistical testing is all about is checking whether the results of your experiment are in line with the predictions of your assumptions. If your assumptions predict something and you get a result that does not jive, it does not match your predictions, that's when we say our predictions were wrong because our assumptions were wrong. We'll go more in depth because this is very important. So what was the size of each sample in the distribution? They were all size 266. What value of P was used to construct it? 0.02, 2%. And what does the bar above 4 represent? It means 16% of our samples, 16% of samples had 4 birds, or had 4 white feather birds, had 4 successes, or 4 yeses. So yes, just because I'm running out of room. Okay. So let's go on further. What is the mean of this distribution, by the way? The mean is 5 birds, right? It seems to be fairly symmetric. Right? It seems to be fairly symmetric, maybe a little skewed on the right, but not too much, so about 5.
I have a question.
Yes.
So if they give us 2% or any percents and we have to find the one that we have to find and they don't match up or they don't work, it's automatically the one they gave us is wrong? How do we know?
So the way it works for this is as follows. You're going to come into a problem with an assumption of what a value is. In this case, we assume that P was 0.02. And then we're going to perform an experiment. Okay, we're going to get the results of our experiment. And what we're going to do essentially is we're going to compare the results of our experiment to what my assumptions predicted. Okay, the 0.02, we're going to compare what we got to what 0.02 predicts. If we get a result that's not in line with what 0.02 predicts, we're going to question whether 0.02 is correct. And we're going to say, you know what? I don't think 0.02 is correct. Somebody is not muted. Somebody is making noise. I mean, I'm making noise, but my noise is okay. Someone else is making noise and it's not okay. Okay. So what is the largest number of birds with white feathers that it is possible to get in a sample of size 266? Not probable, but possible. What's the largest number of birds that it's possible to get in a sample of size 266? Come on, you don't need anything. This is just common sense. If I have 266 birds, how many of them might have white feathers?
266.
All of them, right? 266, right? The largest that I can possibly get is 266. What is the largest number of birds with white feathers that is plausible to get if you have a 2% chance of having a bird with white feathers? And you can use the graph for this. What does the graph say is the highest plausible amount?
6?
No, 6.
13.
13, right? The highest that we ever got was 13, right? So it seems that anything higher than 13 is very unlikely, right? Even 13, we only got like less than 1% of the time, correct? In fact, I might even say that less than 1% is not even that plausible, but we'll keep it there, okay? Now, place an X where the result from the actual sample was located. Place an X where the result from the actual sample was located. That's going to be way out here. And that's not even far enough because if you look at the scale, 43 is way off the page. right? So what approximately is the probability of getting 43 or even more than 43? By the way, that means that our answer of 43 was correct, by the way. What's the probability of getting 43 or even more than 43 birds with white feathers if the assumptions are true? If it really was 2%, which is what we're basing our assumptions on, if it really was 2%, what is the approximate probability of getting 43 or even more than 43? We'll go 43 all the way to 266. Let's look at all of those cases. What's the likelihood of getting 43 or more than 43 birds with white feathers, approximately? Answer, about 0%. It is so close to impossible. It is so far down that it's just not going to happen. And yet we got 43. We got to question something about what we're believing in. And that's exactly the point. We have to seriously question this 2%. That probability, by the way, of getting what you got or even something bigger is called the p-value. The p-value at the end of the day is what we are going to be calculating to determine whether or not the results of our experiments are plausible or not. In this case, our p-value is so small, in fact, I can't even tell you what it is exactly, just to have it. So my calculator gave me 0. In other words, it didn't even bother giving me like a million decimal places. It just was so close to 0 that it just literally just gave me 0. That's how likely it is. So it's really unlikely. Okay. So this is the box. This is the one. Circle it, underline it, make stars around it, and lightning bolts and monster ogre trolls pointing at it, saying, this is important. This is the one. This is the culmination of everything. I mean, we have to do, but like, it's so important, huh?
I have a question.
No question.
Can you give a tutorial on how to draw an ogre troll, please?
It's not an ogre troll. It's two different things. An ogre.
You just said that.
I said an ogre or a troll.
Can you give a tutorial, please?
No, if you don't know how to draw a troll, I can't help you with that. Okay. Now I believe you're just trolling me. Oh, you saw what I did there? That was like perfect.
I'm like laughing.
On the inside, I get it. Okay. So the p-value is the probability of getting a result from a random sample as extreme or even more extreme. That just hurt Wendy. Or even more extreme than the one from the actual sample. If the sample had been taken from a population with a standard p proportion of yes. In other words, if your assumptions are true, the probability of getting the result that you got or something even more extreme is called the p-value. If the p-value is small, typically less than 0.05, 5%, it's quite unlikely to get such a sample from a population with the specified standard. Thus, the result of the study is said to be statistically significant. You want to look carefully at any result that is statistically significant to see if you can understand why such an unusual event happened. Usually, the reason why it's unlikely to have happened, why the p-value is so small, is because your assumptions were incorrect. Of course, you might have made a mistake, or maybe it's just like a really bad sample, but in general, it's because your assumptions are incorrect. In our case, the result from the Chernobyl study is in fact statistically significant because the chance of it happening by the likelihood of it happening by chance alone was essentially 0%. That is such an unlikely occurrence that if it does happen, it's not chance alone in our minds, but rather something else. What is that something else? The fact that our assumptions were wrong. So of course we need a more systematic way of doing this, and we'll get it. So does the study provide convincing evidence that there was a higher rate of these mutations in the barn swallows around Chernobyl after the accident than before? The answer is yes. Okay, it is convincing evidence because by chance alone, 16% would not have occurred. So the fact that we did get 16% means the proportion of birds with mutations is going to be more than 2%. How much more than 2%? That's a whole other question. I just know that 2% was too low. Can I claim it's all the way at 16%? No, can't claim that. But I know it's more than, well, I don't know, but I'm really, really convinced that it's more than 2%. Okay. Example. Test of the validity of natal charts. So professional astrologers prepared natal charts for 83 volunteer subjects. Each subject was given 3 natal charts, their own, and 2 randomly chosen cards that were made for other people. They were asked to pick out the one that most correctly described them. 28 out of 83 selected their own charts. To assess whether astrologers can prepare valid natal charts, to what standard should the results from the sample should be compared? Well, this person can't write English, obviously, but if we're testing whether or not these astrologers are good at what they do, they can actually prepare valid natal charts. To what standard should we compare this to? If professionals can truly do valid natal charts consistently, what percent of them should have been accurate?
100%.
100%. That's the way I read it. So we're going to compare it to 100. We're going to compare it to 100. Okay, so our value of P, not our P value, the value to which we are comparing our sample is going to be 1.00, 100%. What is our sample size?
$83.
83.
How many in the sample were yeses or successes?
28.
28. And as such, what is the proportion of yeses in our sample?
Isn't that 28 over 83?
Right, which is approximately 33.7%.
0.34.
Yeah, that's approximately 34. So we got a value of 34% when we are expecting 100%.
Where did you get the 34% again?
I did.
Divide-
Go ahead, David.
Divided 23, or what is it? Yeah, 28 by 83.
By 83, thanks.
And you get 0.337, round off to the nearest 100.
Right.
Thank you.
You're welcome.
Well, he can say you're welcome. Now, here is a sampling distribution for this situation with the number who selected their own chart on the x-axis. In other words, if we took samples of size 83, actually, 1 second.
doesn't make sense.
I see. Okay, let's go back a second here. I got to fix something. I understand now. I understand now. I have to make a correction. This wasn't 100%. It wasn't 100%. I was trying to figure out what was going wrong here, and I realized
83%.
that we're actually not trying to determine if the astrologers are fake, but we're actually trying to determine if the astrologers know what they're talking about. Okay, we're trying to determine whether or not the astrologers are actually good at predicting things. Okay, if the astrologers have no idea what they're doing, if the astrologers have no idea what they're doing, then what percent of the 83 would pick their own?
0.
Not 0, because some of them are going to get lucky, right? But it should be because you're picking one of 3 each time.
Is it 28?
It should be 33%. No?
How'd you get 33?
Because there's 3. Each subject was given 3 charts, right? Each one was given 3 charts, and you're picking one of those 3 charts at random, correct? Essentially, you're picking one of those 3 charts at random. How often, when you pick 3 things at random, do you get the one that you're looking for? 1 in 3.
1 out of 3.
Right? 1 out of 3, which is a 33%. Correct?
Yes.
Okay. That's the way I'm seeing this. These examples that they're doing are really horrible. Because they're not really explaining.
So that means this chapter should not be on the test.
No, this is an important chapter. It's just- it's
I
really
agree
bad.
with Miriam.
Nice
This
try.
chapter is
No, guys, this is the most important chapter that we've done.
This is this is the
This class is a
democracy. See, we
democracy.
all agree that chapter
Guys.
20.
power of the people.
So,
Guys, please use your voices. We have to vote no on this chapter.
Protest
Yes.
this
No.
chapter.
Everybody
I
type
am
in no.
I am anti-choice for Professor David right now. No
Unfortunately-
chapter.
Well, I
Everybody type in no.
Guys,
Exactly.
guys. Okay. This is a dictatorship, not a democracy. Okay.
Damn. Only 3
So-
people typed in no.
We're going to work under the assumption that P is 0.33. Even if it's not what they intended, we can still do it. So P equals 0.33 is what we expect. Okay. Because if it's truly nonsense, then 33% of the people should select their own chart. Because 1 in 3, every person has a 1 in 3 chance, which means 1 in 3 of them should do it. So we're expecting 0.33. We got, what was 28 out of 83 again?
0.337.
0.337. Okay, so we got something that's very, very close to what we expect. Okay, we expected 0.333 of 83. We expected about 28 people to pick their own chart. If it's nonsense. If it's nonsense, if there's nothing in it that says, oh my God, I need, I mean, this stuff is really accurate and it's so obvious which one is mine. If there's nothing like that, we expect 33%. We expect 28 people. Now, out of 83, what is the largest number that might actually pick their own chart?
83.
83. What's the smallest number that might actually pick their own chart?
1.
Well, 0,
0.
right? What's the largest number of people who select their own horoscope that is plausible to get based upon this graph? Based upon the graph, what's the largest number that is plausible to get?
43.
40. Well, the graph kind of ends at 42, so we'll say 42. And what's the smallest number that is plausible to get based upon this graph?
14, 15.
Yeah, I'd say 15. So place an X where the result from the actual sample would be. We got what, 28? So we got a result right there in the center. In other words, we got a result that is essentially exactly what you would expect if astrologers do not know what they're talking about, at least in this regard. So, what approximately is the probability of getting 28 or even more people who select their own horoscope if the charts really are complete nonsense? Based upon the graph, what's the probability that 28 or more people would pick their own chart? It seems to be about 50%, right? It's like right in the middle of the chart, correct?
Mhm.
That's called the p-value. The name of this is the p-value. This is a very high p-value. Is it more than 5%?
You said it was 50%, so yeah.
It's way higher than 5%, right? Which is usually the cutoff. So that means that this result is not statistically significant, and it can reasonably be attributed to chance alone. So therefore, there is not convincing evidence based upon this particular experiment that astrologers have any skill at predicting whatever a natal chart predicts. I don't know what that is. Is that the future? Is that your kids? What's a natal chart?
Professor?
Yeah.
So just so I'm clear, so if our conclusion is that it's a statistical significance, that means that we're wrong, right?
No, statistical significance means that your assumptions are wrong. Right?
Okay.
That what you're assuming to start the experiment was wrong. We assumed in this experiment that astrologers would not know how to predict anything about the future or whatever it is these things do. And as such, we should get a result around 33%. We did get a result around 33%, which means we're not going to reject what we believe to be true. In the other example, the 2%, 16%, our result was so far away from what we expected that it was a statistically significant event.
So if it's not, we put that it's recently attributed to chance alone. I'm getting confused with the definitions.
Yes, statistically significance is exactly the opposite of can reasonably be attributed to chance alone. These are the two possibilities.
Oh, gotcha. So if we circle the second one, the longer one, that means that our assumptions were correct.
That's well, not that they're correct, but we don't have evidence. We don't have the evidence to say that they were wrong.
Okay, thank you so much.
Not that we did get what we expected.
Yes, we got what
we did get. So that means that it can easily be attributed to chance alone.
Exactly.
Whew, that's so good.
Okay. So does the experiment provide convincing evidence that a person's own natal chart describes them better than randomly selected ones? The answer is no, it does not. Random selection is no different than their own. Okay, if you just pick one at random, it's just as likely to be correct than if you're given one straight up. Okay. Let's try another one. Hopefully this is a better example. Chimpanzees were given the choice of pulling one of the two heavy rakes toward them. Pulling one of the rakes would bring food with it, and pulling the other would not bring in food. And the correct rake was randomized. It wasn't always the same one. The researchers found that the correct rake was chosen significantly more often than would be expected by chance. So this particular experiment, they had a p-value of 0.01. Okay, their p-value was 0.01, which is less than 0.05, the cutoff, the standard cutoff. A p-value of 0.01 is low enough that we reject our assumptions. Now, what is the assumption in this case? What is the standard against the sample that is being compared? Well, if the chimpanzees did not pull the one with the food more often, then how often should they pull each one? What is the most reasonable assumption to make?
50-50?
50-50, right? We're trying to compare it to 0.5. 0.5 is what we would expect if they just pull one randomly. So the p-value was 0.01. That means 1% of our samples, or let me rephrase that. Um,
It's not 1/10. Oh no, no, you're right.
oh, no, it's 1%, but let me
1%.
rephrase how I want to say
Yeah.
this. In our sample, in our sample, the number of times that the rake with food was pulled was so high that the likelihood of the chimpanzee pulling that many by chance alone was 1%. There's a 1% chance. There's a 1% chance that the chimpanzee accidentally just happened to pull the one with the food as many times as it did. Would you, if something happened that had a 1% chance of occurring, would you say, oh yeah, that's reasonable? Is a
No.
huh? To yes or no?
It's a slim chance.
It's a slim chance, right? There's a 1% chance of having the chimpanzee pull the food that many times if it was really a 50-50. Think of it in terms of coins. How many coins would you need to flip for you to get all heads and have a 1% chance of it occurring? Let's take a look. If you flip one coin, what's the chance that it's a heads?
50-50.
50-50, 50%. If you flip two coins, what's the chance that they're both heads?
50-50.
No,
5.
no.
100.
100% that they're both heads? That's the only possibility is both heads?
5%?
I don't know.
Someone say 5?
25?
25% is correct. 1 in 4. Because there's 4 possibilities. 2 for the first, 2 for the second. 2 times 2 is 4. That's 25%. If you flip 3 heads, what's the likelihood that they're all, sorry, 3 coins. What's the likelihood that they're all going to be heads?
You would do 1/2 times 1/2 times 1/2.
Amazing. 1/8, 12.5%. If you flip 4 coins, you would do 1/2 times 1/2 times 1/2 times 1/2. That's 1/16, which is 6.25%. If I did 5 coins, 3 point something percent. If I did 6 coins, still more than 1%. If I did 7 coins, finally, 7 coins gets me a value under 0.01. So the likelihood that the chimp, basically what we're saying is that the chimp flipped 7 heads and got, 7 coins and got 7 heads. Not an impossible event, but an unlikely event. Okay, if it's really 50-50. Now, if you flip the coin 7 times and get 7 heads, what might you start thinking about your coin?
You might think you have good luck.
Okay, that's one possibility.
Also, it's not a good coin.
Or it might not
because
be a good coin, right? It might be weighted, right? That it's not really 50-50 after all.
I think you would want to do law of large numbers and flip it at least 50 times.
Because she loves the law of large numbers. What can I say?
I love it.
So what do you think the researchers concluded in this example? What do you think their conclusion was? What was their conclusion?
Wait, are we still talking about the coins or the example?
No, this example. What do you
Okay.
think their conclusion was? Not a math conclusion, a physical conclusion. What do you think they concluded?
That's a slim chance that it.
No, not math, not math. What do you think they concluded physically?
So the chimps are more likely to choose the rake with the food because it brings them food.
Well, yeah, the chimps were able to recognize food.
Chimps were
Right?
able
The
to
chimps were able
recognize.
to recognize where the food was and how to get it. Right?
Oh,
The
this
chimps
goes
were-
back to the elephant with the eggs. The
It's the
egg.
same thing. I just
how
didn't use the
humiliating.
example, right? I didn't really understand what they were saying.
This one's a little less humiliating
This one's a little less humiliating.
for
Okay,
the elephant.
fair enough. All right, so let's try this one. Significant testing in education. California tests all fifth grade students on physical fitness. 63% of fifth graders have an aerobic capacity that is considered healthy. Suppose that at your school, 30 of the 65 fifth graders have an aerobic capacity that is considered healthy. Is the difference statistically significant? So is our result for our school just, okay, every school's going to be different, but yeah, it's possible? Or is the result so unlikely that we have to reject it? Okay, so let's start. First, what is the sample size here?
65.
65. We have 65 fifth graders in our sample. How many yeses do we have in our sample?
30.
30. What's the proportion of yeses in our sample?
30 out of 65.
Which is about
0.46.
0.46.
Wheat or white bread. Okay.
Now, we are testing whether our school conforms with California. So what are we testing against?
The the 63%.
63%. Our result of 0.46 seems pretty far away from 63%. Is it far enough away from 63%? That's the question. Well, let's scroll down and see what comes next.
What do you mean it seems far away?
Well, it's a 46 and 63 is 17% away. That's a big difference.
That doesn't seem that big to me, but I don't know.
Well,
When statistics are involved, it's big.
yeah, 17% is pretty big. So let's take a look at what comes next. So let's scroll down. So here is a sampling distribution. Okay, this is again based on the assumption that 63% is correct. If 63% is really correct, our sampling distribution would look like this. What is the largest number of fifth graders who have healthy aerobic capacity that it's possible to get in a sample of size 65?
53.
65.
65,
Oh,
right?
65. I'm sorry.
What's the smallest number in a sample of size 65?
0.
About
0, right?
50.
You can have 0,
0.
correct? Okay. What's the largest number that is plausible to get based upon this graph?
About
53.
54.
About 54. And what is the smallest number that is plausible to get based upon this graph?
36
No,
or 63.
20.
29, it looks like.
29, 28. Yeah.
29. Place an X where our sample is. What was it for our sample again?
30. No, wait.
We had 30, right? 30 out of
Yeah.
65.
Yeah.
So our value is right there. Okay. Now, what approximately is the probability of getting 30 or even fewer who have healthy aerobic capacity in a random sample of 65? So I'm going to do it on my calculator here because I have the possibility of doing that. And I'm just going to give you the answer. So this is a binomial CDF. And
So the numbers you're dividing are which ones?
I'm just doing it on my calculator, so don't worry about the details. I'm just doing it on my calculator here. So
You have to show me how to do that.
p-value. No, you don't have to. Just the results. And we're
Yeah.
assuming what was the 0.63, right?
Yeah.
Okay, so my probability, just so you know, I just calculated it, was 0.004. The likelihood of getting the result that I got, or something even more extreme, was less than 0.5%. That's the p-value. That's the p-value. So, is the result from our sample statistically significant or not?
No.
Huh?
Statistically significant, it's significantly high then.
It's significantly low.
No.
The less than 0.5% is
Yeah.
what you're saying. It's
Yeah,
less than.
our p-value is less than 0.5%. Less than 0.5% of a p-value is very, very small. In other words, it is statistically significant. It's less than 0.05, our normal cutoff, unless we have a reason to say otherwise. It is statistically significant, which tells me that the kids in my school are not getting enough exercise. And if I was doing this study, I would say to my school district or to the principal, whatever, you have to have more physical education or this or that to remedy the situation.
What's
Because
the name of the probability?
it's the p-value.
Oh, what is the name for this probability? The p-value?
Yeah, everything's the p-value. We're always calculating the p-value.
All right.
P-value-
Is this result from the sample statistically significant, or can the result reasonably be attributed to chance alone? It's statistically significant.
It is statistically significant. It is not a result that can be reasonably attributed to chance alone.
Yes.
I have a suggestion.
Yes.
I think the school could benefit from this woman. I don't know if you've heard of her, Michelle Obama.
No,
She
never
likes to do healthy kids.
She
So maybe
likes
they
to do
could work
healthy
out
kids.
with her.
She likes to do healthy kids. What do you mean she likes to do?
To
Oh.
help.
We do not make pedophilia jokes here.
Yeah,
no, I wasn't making it. That wasn't
David
a joke.
Berkowitz?
No,
No.
that was
This is
not.
being
Sorry,
recorded.
it was worded incorrectly. I'm standing behind the professor because that
So
was
now
worded
we're playing
wrong.
girl.
Okay, wait. I'm kidding.
I
I'm
don't think
kidding. I'm
so.
kidding.
I was
Oh,
not
yeah.
making, guys. I
No
was
one is
not
suing
making that joke.
David.
I was asking what you meant. That's all.
Yes, so I will explain. Michelle Obama, for
Yeah.
example, likes to have kids eat healthy lunches. For example, maybe replace a cookie with an apple. That is one thing that she does.
I
She
see.
might also want to work out with you and the children.
I see. Well,
Honestly, go Michelle. Like,
go shell. Okay, that's fine. But I'm gonna have that cookie because I'm fat and I like to eat. But let's move on, anyways.
I have a quick question. I'm so sorry.
And that
Go ahead.
cookie, that
How did you find the 0.004 again?
I did it on my calculator. You're not going to be required for that because you don't have the math yet for it. I just did it on my own.
Okay.
I can tell you how to do it on your calculator if you like, but the problem is that every example is going to be different. And what I did for this example might not necessarily hold for the next example.
I'm only on a need to know basis.
It's only on a need to know basis. And unfortunately, you just don't need to know. What can I say? I'm just kidding.
it's on YouTube if you need to do it.
And everything's on YouTube.
Yeah.
Everything's on YouTube eventually. Okay. So significance testing actually, you know what? I have.
We're going to English.
No, we can do one last case. Okay. Significance. What was that in English? What? Never mind. Okay. Significance testing in cases of possible discrimination.
We're going to English.
What is that?
Somebody needs to mute.
So tests of significance often are used to determine whether there is a statistically significant evidence of possible racial or gender preference. Let's read this example. An important 1977 U.S. Supreme Court case, Castaneda versus Partida, was explicitly decided on statistical evidence. A grand jury decides whether a person will have to stand trial. Of the 800, well, you read it for a second. Go ahead and read it because I'm just going to read what exactly you're saying right there. So go ahead and read it.
Come in. I'm sorry. I'm
Hold
sorry. I didn't mute myself.
So let's start writing what we have here. What's our n going to be in this example?
870.
870. What is our x? How many successes do we have?
I lost track.
Well, read it again. Sometimes you read a problem multiple times because information that you missed the first time around, you catch in the second time around. What is the x in this example?
That is my higher order cognition.
I don't know what those words mean. Those are too long for me.
Would it be 339?
339, excellence, which means our p hat is equal to what?
Do we divide those two?
Is successes divided by trials. So I got 39%. What is the value that we are comparing it to?
79%?
79%. In other words, census figures show that 79% of the country's population had Spanish surnames, but yet only 39% of those who were summoned to serve as grand jurors were Spanish. So he felt that he was treated unfairly because of this, because they might be racially biased against him. Is that result statistically significant? And the answer is, well, here's the sampling distribution. Okay, if 79% was correct, we would be right here, which makes sense. Where were we actually? Our actual value was what, 39%? Sorry, it was how many successes? Was 339. So where on this chart is 339?
Not even on there.
Not even on there. It's so far off the chart that we get a statistically significant result.
Retrial.
Exactly.
So he won his case.
So he won his case. That's what they're saying here. You can actually look it up probably. 1970, he went to the US Supreme Court. He said, listen, I was treated unfairly. The chances of me getting a juror like that was so small that it could not have happened by chance alone. And he won his case. Okay, I have to go a little early today because I have to take a quiz in my chemistry class at 3:15, so I got to prepare. We finished the chapter, which was fantastic. And I want everyone to have a wonderful, 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 wonderful Thanksgiving.
Happy
And
Thanksgiving.
Happy Thanksgiving, everybody.
Happy Thanksgiving, everybody. Stay
Don't
safe.
go out. Stay
Happy
inside.
Thanksgiving.
COVID
Stay
don't
safe,
happen.
everybody. Lori, be careful.
Yes, kiss.
Lori, be careful. Love
Thank you, you too. Kiss math baby for me.
Mr. Hernandez, you too, be careful. Bye, you guys.
Go eat a piece of
Bye.
pie.
It's an age thing, isn't it? That's what it is. I'm just kidding.